And we'll share my screen. Okay, so today what we're going to do is we're going to look at a couple of examples of linear programming problems. Actually, there's three things I want to go over, and then the rest will be pretty much open time for us. One is I want to look at using Excel, the solver function in Excel to do these linear programming problems. Now that I've made you do them for a week, I'm using the brute force method. Let's look at some shortcuts, how technology can help us. So I'm going to throw out an example. This is actually a problem from your homework, but it might have slightly different numbers than what you had in yours, because this is an algorithmic problem. So we're going to look at the Oz Lion Food Company. And they're going to use two types of meat in their lion food. They're going to use giraffe. And giraffe meat contains 18 grams of protein and 36 grams of fat per pound, and costs $2 per pound. The other type of meat that is used is gazelle meat. Gazelle meat has 36 grams of protein per pound and 18 grams of fat, and costs $4 per pound. What we want to do is we have constraints here. We want to have at least 25,200 grams of protein and at least 37,800 grams of fat in the food for a lion. And of course, our objective is to minimize the cost. In that cost function, C equals, if we let X be the amount of giraffe meat used and Y be the amount of gazelle meat used, it's $2 times X times the pounds of the giraffe meat, plus $4 times Y, 4 times the pounds of gazelle meat. Subject to our constraints. So the first constraint deals with protein. The amount of protein from giraffe is 18 grams per pound times X pounds. The amount of protein from a gazelle is 36 grams per pound times Y pounds. And we want that to be greater than or equal to, so we want it to be at least 25,200 grams. And our second constraint is for fat. We have 36 grams per pound for giraffes times X pounds of giraffe meat, plus 18 grams per pound for the gazelle times Y pounds of gazelle meat. And we want that to be at least or greater than or equal to 37,800 grams. So here is a linear programming problem. Now this is actually a standard minimization problem. It could be solved using converting it to a maximization problem and using those surplus variables rather than slack variables. That's the methods in section 5.4 in the textbook. But those are very tedious and, to be honest, a little bit confusing. To be totally honest, I don't use those methods in anything I do. I convert them to a standard maximization problem and solve them, or I use technology just like we're doing here. So I am going to go to Excel here for a second. And in Microsoft Excel, there is a function called the solver. When you do your add-ins, many of you did the data analysis add-in at the beginning of the semester. If you go to data, you go over to the right side, you'll see data analysis, and right underneath it, you'll see solver. If you don't have that, you just have to go to your add-ins and added in, and it'll stall automatically. So what we're going to look at here for this problem involves giraffe meat, which is our variable x, and gazelle meat, which is our variable y. The amount of each, that's x and y, but we're not going to put the variables in there because we're going to let Excel put numbers in there. We want Excel to find x and y for us, so we're going to leave those blank. And then we're going to put in a line for each constraint. Protein is the first constraint. There's 18 grams of protein in the giraffe and 36 grams of protein for the gazelle. So we need to write this in an equation. So the equation here was the amount of protein per pound for the giraffe times the number of pounds for the giraffe, plus the amount of protein per pound for the gazelle times the number of pounds for the gazelle. Now, right now, that's going to be 0 because these two variables, these two cells have nothing in them. Now, this part is not part of the Excel calculation. This is just a note for myself. I'm going to make a note that I want that to be at least 25,200 pounds. That's just so that I can look back later. These two things I'm going to put in here are going to be strictly for me to look back later, so I don't have to search back to the original problem. I have that information referenced, so I can just type it in. Second constraint was about fat. There's 36 grams per pound for the giraffe and 18 grams per pound for the gazelle. So our total fat would be the amount of fat per pound for the giraffe times the number of pounds of the giraffe, plus the fat per pound for the gazelle times the number of pounds of gazelle meat. Again, that's 0 right now because these are left empty. I'm going to make a note for myself again that I want this to be at least 37,800 grams. And then I'm going to put in my cost. This is my objective function. It's $2 per pound for giraffe and $4 per pound for gazelle. So the total cost will equal $2 times the pounds of giraffe meat plus $4 times the pounds of gazelle meat. And we want to minimize this. And again, to minimize these three cells here are just notes for myself. I could have just as well left those blank and referenced back to the original problem, but I put those in there so that when I go to do the actual solver here, I have that information. I don't have to go digging for it. So this is the solver. I'm going to reset everything here, clear everything out. That clears everything. And I'm going to work top to bottom here. This first is set the objective. So I'm going to click there. It's asking me what cell contains the objective function. Well, the objective function was the cost. That's this cell right here. So I click on it and notice it puts D5 in there. And we wanted to minimize that cost. So I'm going to click min here. We're going to do that by changing which cells. So this is telling me what cells are going to be my X and Y variable. So I click there so that that's blinking. I just come over here and I highlight those two cells and it puts them in. So that's going to be my X and Y variables. Excel is going to change those. Then I'm going to go down here and click my subject to the constraints. Notice I highlight that. Now I'm going to click add to add constraints. My first constraint is protein. This is the cell that describes the total protein. So I click on it. I want to be at least, so greater than or equal to. And that's why I put this in here so I don't have to go back and look for it. 25,200. I'm going to add that constraint. Next is my constraint for fat. So I click on this cell, make sure that's blinking. Click on the fat, the formula for fat here. I want that to be at least, so greater than or equal to the 37,800. I'm going to add that, and then I'll click cancel to say I've got them all in. So those are my two constraints. That's the one for protein. That's the one for fat. Everything is in here now. I need to make sure the settings are correct, or right. Make unconstrained variables non-negative. That's just standard. That's saying those are those trivial constraints that everything is greater than or equal to 0. I want to make this a simplex linear programming. So simplex LP, I want to make sure that setting is there. I'm just going to click solve. I was going to say, hey, we're going to solve this for you. Do you want me to put the numbers in, or do you want to go back to the original? If I click restore original, it's just going to put it right back to where we started. So really what I want to do is I want to keep the solver solution so I can see what it actually solved. So I click OK. And you can see here it's saying 933 1/3 pounds of giraffe meat, 233 1/3 pounds of gazelle meat, It's going to be a cost of $2,800. So that's our optimal solution. That is the minimum cost to get these requirements that we want here. Now, the next thing I want to address is something called shadow cost, or what this textbook calls shadow cost. Shadow cost, in economics, would be called marginal cost, the cost of one more. So shadow cost here is, and there's a shadow cost for each of the constraints. So our first constraint is protein. I find the shadow cost for protein. I'm going to change the constraint by increasing it by 1 unit. So what that means is I'm going to go to my solver here. This is the constraint for protein. So I'm going to click change here. And I'm going to change this from being greater than or equal to 25,200 to 25,201. So I'll click OK. And notice it changed that to 25,201. I click solve. And notice this was 2,800 before for the cost. It is now 2,811 cents. So the shadow cost for protein, it increased by increasing the need for protein by 1 unit, and increased the cost by 11 cents, or 1/9 of a dollar, I believe is the way that WebAssign was expressing it. Well, let's look at fat, the shadow cost for fat. So what we're going to do is we're going to go back to our solver, and we'll change this constraint back to 25,200, back to what it was before. Notice it's back to what it was. This constraint now has to get changed. This is the constraint for fat. I'm going to click change, make that 37,801. I increased the limit on fat by 1. So you see that's changed now, and I'm going to click solve. Well, you notice the price is still 2,800. It did not change the price at all. So increasing the constraint for fat by 1 unit does not change the price at all. So the shadow cost of fat is $0. Increasing it by 1 unit does not change the price, the optimal price at all. So there's 0 shadow cost of increasing the fat at that point. Now, if you kept increasing it, there eventually would be, because it would require at least another pound of one of the two or both of the types of meat. But for just one above the existing constraint, the shadow cost is 0. So again, in economics, that's often called marginal cost, but it's the cost of just 1 more unit of that type of item in that constraint. So the next thing I want to do is we're going to go back to Word here. And I'm going to look at a dual problem. Now I'm going to put the problem out here, and then I'm going to go ahead and I'm going to go back to Excel and show you how quick and easy it is to solve with Excel. And then we're going to go ahead and solve it actually using the duality and the process of solving a dual. So the problem I'm going to put up here is solve using duality. I'm going to minimize cost equals 2x plus y plus 2z. Subject to 3x plus 2y plus z greater than or equal to 100. 2x plus y plus 3z is greater than or equal to 200. Now, first thing you'll notice, the reason duality can apply here, first of all, this is minimize. Second of all of our constraints are greater than or equal to. Of course, we do have the trivial constraints here. X is greater than or equal to 0. Y is greater than or equal to 0. Z is greater than or equal to 0. Those are the trivial constraints. The unconstrained variables are all non-negative. Now, one problem that comes here, if you're thinking back to systems of equations, here we have 3 variables and we only have 2 constraints. So that makes some major issues as far as trying to solve this. We can still do it, it would just be a little more difficult. one of the variables ends up being a trivial variable. Anyway, let's look at how we would solve this with Excel first, before I dig into the brute force method of duality. So we're going to go to Excel here, and I'm just going to put X, Y, and Z here. No fancy names for those. And these three cells are going to be the values for X, Y, and Z. So the first constraint, I call it first, is that 3x plus 2y plus 1z, I want that to be greater than or equal to 100. So let's put in the formula here. This is going to equal 3 times the value of x plus 2 times the value of y plus 1 times the value of z. And again, that's going to be 0 because right now we have no values in there for the variables. My second constraint is 2x plus 1y plus 3z, and I want that to be greater than or equal to 200. So again, I'll put in this formula equals 2 times the value of x plus 1 times the value of y plus 3, oops, get back here, 3 times the value of z. And again, that'll be 0 because there's no values for x, y, and z right now. Our objective is to minimize 2x plus 1y plus 2z. So this is going to be equals 2 times the value of x plus 1 times the value of y plus 2 times the value of z. So that's my objective function there. So we'll go to solver. We're going to clear this out. We'll hit reset all. My objective here, shrink this down just a little bit. Well, not me right now. So my objective here, I am going to click on this cell right here is my objective. And I want to minimize that value. So I click on minimize by changing these three cells, X, Y, and Z, subject to the constraints. So I'm going to add my first one. This value has to be greater than or equal to 100. So that's my first one. And this value here has to be greater than or equal to 200. I add that in, and I click cancel to say that's all of them. Make sure I change this to simplex LP, and I hit solve. I hit OK. And you can see right there, it gives us the minimum value there. X is 0, Y is 20, Z is 60, which will have a minimum cost of 140, and meeting my constraints exactly. At least 100 for the first one, at least 200 for the second. That was pretty simple to solve that. Literally a matter of minutes. If you get good at typing these formulas in, the key is you just put in the coefficients here. You'll leave a blank row here for the variables, and then these are the formulas for those coefficients go here. And so this is actually your first constraint, second constraint in your objective function. This is just values that are the coefficients of each of those variables that you use to set up those equations here. Well, let's go back now to Word and look at solving this with duality. So that problem that literally took 4 or 5 minutes with Excel, let's see how quick we can run through it with duality. I shouldn't say run, but I'll take my time and make sure you guys can keep up on it. So we start out by creating a characteristic matrix. Characteristic matrix starts with the constraints. So my first constraint here, and all I'm going to put in is the coefficients, 3, 2, 1, and 100. Very similar to what I put into Excel, except I don't have that blank spot here for to put the formula in. I use the second constraint, which is 2, 1, 3, and 200. Again, all of these must be greater than or equal to, or we cannot put them in here as a dual. And then I put in my objective function with this replaced with a value of 0. So 2x, 1y, 2z, so 2, 1, 2, and I put 0 in there. This is my characteristic matrix for this LP problem, for this minimization problem. Next, we're going to find the dual. And to find the dual, we're going to what's called transpose the matrix. So the first column becomes the first row of the matrix. 3, 2, and 2. Second column becomes the second row of the matrix. 2, 1, and 1. Third column becomes the third row. 1, 3, and 2. And the final column becomes the final row. 100, 200, and 0. This is the new objective function. It is now to maximize that function. And that is going to be P here equals 100. Now we don't want to use X now. We'll use S and T. So we're going to maximize, instead of minimizing C equals 2x plus y plus 2z, we're going to maximize P equals 100s plus 200t. And we're going to go subject to the constraints. All the constraints now are going to be less than or equal to. Up here, they're all greater than or equal to. In the dual, they will all be less than or equal to. So this one is going to be 3s plus 2t is less than or equal to 2. This one will be 2s plus 1t, or just t, is less than or equal to 1. And this one here, 1s, or just s, plus 3t is less than or equal to 2. So those are my constraints. So let's set this up with slack variables now. I have 3s plus 2t plus, now my slack variables are going to be the variables from the original LP problem, from that dual. So I'm going to put in plus x equals 2. Notice I took out the inequality and I added x to make both sides of that equal. My second constraint is 2s plus t. I'm going to add y as my slack variable to make that equal 1. And for my third constraint, it's 1s, or just s, plus 3t. And I'm going to add z as my slack variable to make that equal 2. And then for my objective function, I move everything over to the left side, so that's negative 100s, negative 200t, plus p equals 0. So I fill in my zeros here. And I will create now my initial tableau. So my initial tableau is going to be S, T, X, Y, Z, and the constants. So row 1 here is going to be, this is going to be the X row because X is my slack variable. It'll be 3, 2, 1, 0, 0. Oops, I got to put my R column in here yet. That's my R or P or whatever you want to call it. 0, and then my constant here will be 2. My second row is going to be my Y row because Y was my slack variable. That's 2, 1, 0, 1, 0, 0, 1. My third row is going to be the Z row, row Z. The Z was my slack variable, so 1, 3, 0, 0, 1, 0, 2. And finally, my fourth row is my row P or row R, whatever you want to call it, with the negative 100s, negative 200 for T, 0, 0, 0, 1, and 0. So now we need to solve this tableau. We need to reduce the tableau. Remember, to do that, this is a standard maximization function or problem. So I'm going to look at this bottom row and I look at any negative values. I have two negative values, negative 100 and negative 200. So I start with the smallest negative value, or the most negative value, the one of the largest absolute value, which is furthest from 0, which will be the negative 200. I then look at my test ratios for the rows in that column. So I take my constant, in this case 2, times the value in my pivot row. 2 divided by 2 is 1. For row 2, it's 1 divided by 1. Well, that's also a test ratio of 1. Row 3, it's 2 divided by 3. That's 2/3. That is my smallest test ratio. So 3 is going to be my pivot. I'm going to pivot around that number 3. Now I am already pivoting the column.
The bean flipper?
What's that?
Oh, you're the bean flipper.
Must have been mistaken. No, I'm going to use that 3 now to eliminate
You close that
everything else in
window,
that,
shade three like up.
that column.
Tilt them up. I don't like when people can see in here. The people are walking. No, just do it.
Yeah, microphone's off mute, Ryan.
Oh, I'm sorry.
No problem. So we need to eliminate everything else in that row. So let's start with row 1. Let's get rid of that 2. We're going to multiply row 1 by 3 and row 3 by -2. I'm asked, why didn't we do -3 and +2? Because we want to keep the row that we are eliminating, we want to keep that row positive. So row 1 times 3, 3 times 3 is 9, 2 times 3 is 6, 1 times 3 is 0. The zeros, sorry, 1 times 3 is 3. The zeros stay the same. 3 times 2 is 6. So we've adjusted row 1. Row 3 is times -2. So 1 times -2 is -2. 3 times -2 is -6. The zeros stay. 1 times -2 is -2. The zero stays. 2 times -2 is -4. So let's combine those. So I've got S, T, X, Y, Z, R, and constant. Row 1, it's still going to be row X, but I'm going to combine 9 and -2 makes 7. 6 and -6 makes 0. Now that's the big one. We wanted to zero that one out, so that's good. Yeah, 3 and 0 make 3. 0 and 0 make 0. 0 and -2 make -2. 0 and 0 make 0. 6 and -4 make 2. So we replace row 1. Now I'm going to remove these temporary values. I don't have to remove them in row 1 because we're done with that. But I do have to make sure I remove them in row 3 because we're going to reuse that row. So now let's look at row 2. I want to zero, it's still going to be row Y, or the Y row. I want to eliminate this 1 using the 3. So I'm going to multiply row 2 by 3 and row 3 by -1. So 2 times 3 is 6, 1 times 3 is 3, 0 stays, 1 times 3 is 3, 0 stays, 1 times 3 is 3. In row 3, -1 times 1 is -1, -1 times 3 is -3. Again, those two add to 0, which is what we're shooting for. 0 stay, -1 times -1 is -1. 0 stays, 2 times -1 is -2. So let's combine. 6 and -1 make 5. 3 and -3 make 0, which is what we were shooting for. 0 and 0 makes 0. 3 and 1 makes 3. 0 and -1 is -1. 0 and 0 makes 0. 3 and -2 makes 1. So again, I'm going to go back and I'm going to erase those temporary values. Now, row 3 is our pivot row. So the numbers are not going to change, but remember in the pivot row, the name changes. We take the name of our pivot column and replace the name of the pivot row with it. So this is going to become row T now. The values are still 1, 3, 0, 0, 1, 0, 2. Notice those values did not change. Row 4, we have to again zero out. It's going to stay the row R, or the R row. We have to zero out the -200 here. So what I'm going to do is I'm going to multiply row 3 by 200 and row 4 by 3. So 1 times 200 is 200. 3 times 200 is 600. 0 stay. 1 times 200 is 200. 0 stays. 2 times 200 is 400. Row 4 times 3. 3 times -100 is -300. 3 times -200 is -600. The zeros stay. 1 times 3 is 3, and the 0 stays. So we combine those rows. 200 plus -300 is a -100. 600 plus negative 600 is 0. Again, we needed to zero out that cell. 0 plus 0 is 0. 0 plus 0 is 0. 200 plus 0 is 200. 0 plus 3 is 3. And 400 plus 0 is 400. There's our new tableau. Notice in our bottom row, we still have a negative number, that negative 100. So that is going to be our pivot column. Let's once again do our test ratios. So we got our constant divided by the value in the pivot column. 2 divided by 7. Now, 2/7 is a decimal is 0.2857114 approximately. 1 divided by 5, 1/5 is about 0.2, so it's a little bit smaller. And 2 divided by 1 is just 2. So our smallest test ratio here is the 0.2. 5 is going to be our pivot for this table, for this tableau. So we're going to use that 5 to eliminate the other values in that column. So let's set up my next tableau. S, T, X, Y, Z, R, and constant. Oops. And let's do row 1, which is going to stay labeled row X. I need to get rid of that 7 by using the 5. So I'm going to multiply row 1 by 5 and row 2 by negative 7. Again, I want to keep row 1 positive because that's the row I'm replacing. So multiply by 5. 7 times 5 is 35. 0 stays. 3 times 5 is 15. 0 stays. Negative 2 times 5 is negative 10. 0 stays. 2 times 5 is positive 10. Negative 7 times row 2. 5 times negative 7 is negative 35. That's good because we want those two to cancel out. 0 stays. 3 times negative 7 is negative 21. Negative 1 times negative 7 is positive 7. 0 stays. 1 times negative 7 is negative 7. So now let's combine those two rows to replace that row 1. 35 and negative 35 is 0, which is what we wanted. 0 plus 0 is still 0. 15 plus 0 is 15. 0 plus negative 21 is negative 21. Negative 10 plus 7 is negative 3. 0 plus 0 is 0. 10 plus negative 7 is a positive 3. Row 2 is our pivot row, so the numbers are going to stay the same. But remember, we take the name of the pivot column and we replace the pivot row with that name. So this will become row S now. The numbers will stay the same. 5, 0, 0, 3, negative 1, 0, and 1. We're going back to those original values. Should have probably erased these temporary values before I did that, but you know that those were just temporary. Get rid of those quick. And now we're down to row 3. In row 3, we need to eliminate the 1 here with the 5. So I'm going to multiply row 2 by negative 1 and row 3 by 5. So row 2, this becomes negative 5, 0, 0, negative 3, positive 1, 0, and negative 1. I just multiplied everything by negative 1. Row 3 is times 5. 5 times 1 is 5. 3 times 5 is 15. 0, 0, 1 times 5 is 5. 0, 2 times 5 is 10. So let's combine those to get our new row 3. And this is still named row T. Negative 5 plus 5 is 0. 0 plus 15 is 15. 0 plus 0 is 0. Negative 3 plus 0 is negative 3. 1 plus 5 is 6. 0 plus 0 is 0. And negative 1 plus 10 is 9. And we need to go to row 4, the P row or R row, whichever I want to call it here. And in this row, I'm going to erase my temporary values here again. I want to get rid of the negative 100 here. Again, I'm using the 5 up there. So I'm just going to multiply row 2 by 20. 20 times 5 would be 100. I'll add the negative 100 to make 0. So I don't need to multiply the row 4 by anything. I'm multiplying it by 1, but that won't change anything. So multiplying row 2. 20 times 5 is 100. The 0 stay. 20 times 3 is 60. 20 times negative 1 is negative 20. 0, 20 times 1 is 20. And let's combine those two rows. 100 times negative 100 is 0. 0 plus 0 is 0 for both of the next two columns. 3 plus 0 is 3. I'm sorry, 60 plus 0 is 60. Negative 20 plus 200 is 180. 0 plus 3 is 3. And 20 plus 400 is 420. Now, this bottom row is all positive, which means we're done. Now, our solutions read out a little bit different here. For x, we take the value at the bottom of the x column, which is 0. We divide it by the value at the bottom of the r column, which is 3. 0 divided by 3 is 0. For y, we take the value at the bottom of the y column, which is 60. And again, we divide by the bottom of the r column, which is 3. 60 divided by 3 is 20. And for z, take the value at the bottom of the z column, 180, divided by the value at the bottom of the r column, the 3. So 180 divided by 3 gives us 60. Our minimized value is the value here at the bottom of the constant column divided by that column there. 420 divided by 3 is 140. Now, if I go back to Excel, we'll see, yes, it was 0, 20, and 60 for X, Y, and Z, and 140 was our minimized value. So the duality does allow us to solve that, but you can see that took 20 minutes, whereas punching it into Excel took 4 or 5. Now, I'm not one to encourage you to blindly use technology and not understand how to do stuff. But full confession, I do use a lot of linear programming, and I do it if it's a simple 2-variable constraint. I will do it out by hand just because I don't have to go back to my computer. If I have a piece of paper and a pencil available, I can pretty quickly sketch it out and solve it, without having to make my way back to an office and a computer. If it's 3-variable, to be honest, outside of the educational setting, I have never used a Tableau in my life to solve a linear programming problem. I have always used technology like Excel or Minitab or other softwares out there that are designed for it. There are softwares that are better than Excel. Excel is a little clunky, but if you get good at programming this in, you can see it took a couple of minutes to program it in, another minute or two to set the solver, and there was your solution. Like I said, I hate to encourage you to not understand the calculations. I do want you to understand the calculations, but just the simple 2-variable linear programming is really all you need to be able to do by hand. The 3-variable stuff, if you can get good at using this solver function in Excel, not to mention the fact the final test is timed, so if you can use this solver function, it'll make a huge difference on how much you can accomplish on that final test. There are a few linear programming problems on the test. That's about all I will say about how the problems are broken down. There is one problem involving duality, so you do need to either be able to use duality, or the problem on duality can be put into Excel just like this. Rather than finding its dual, you can do exactly what I did here and solve it using Excel. Personally, that's the route I would go. Like I said, I feel like I'm encouraging you to not do the math, but really, I'm an engineer. My background is engineering. I'm more about results and practical side of it. It's not something you're ever going to do by hand outside of the educational setting. Like I said, other than the simple 2 variables. Okay, I'll shut up now because I feel like I'm trying to talk you out of learning something. Does anybody have any questions? I know there's a couple of problems you wanted me to go over.
Hey, can we use the Excel to do to maximize it too?
Yes, Excel will maximize. To do that, you would just use, when you go into the solver, you just click max here, so it'll maximize the value in that cell instead of minimize it.
And then we change our constraints to greater than or equal to?
For maximizing, they would usually be less than or equal to.
That's what I meant. Sorry.
Yep. But yeah, you can use Excel for the simple 2-variable linear programming problems as well. Those I would like you to see you, even if I totally understand if you don't do them by hand on the exam because of time, because even the 2-variable ones do take a considerable amount of time. But to at least be able to understand how to graph them and find that feasible region and use the corners, I'm okay with that. I'm okay with you using Excel to do all of the linear programming problems on the exam, as long as you understand those basics of the 2-variable. Any other questions? Okay, well, I'm going to shut down the recording and I'll hang out here.